Hi there, this is Dr. John. Welcome back to another pulley problem, part 3, as we get more and more complex in our evaluation of pulleys. We have a table here with two different masses, a pink and a blue one, and a green mass hanging off the table with a pulley. This one has three masses, two tensions. So it has tension number 1 here in the blue rope, tension number 2 in the red rope. We're supposed to find both tensions and the acceleration. So there's a lot to find. We obviously have three masses, so the chances are we're going to have three equations, three unknowns, because as I said, we have three different things. Again, in this kind of problem, we want to go through the same system that we've done before for the first two videos. First of all, we want to assume a direction for acceleration and then isolate each mass and see what the mass times acceleration, what the total force, and what the acceleration is going to be of that specific mass. Let's take a look at that. Let's start off by assuming an acceleration. If you take a look at this, you realize both these masses are on the table. They're not spontaneously going to move that way. Either this thing's going to pull it downward or it's not going to move at all. And since this is a frictionless surface, it's going to go downward, which means we can assume an acceleration. It's in this direction. So that's the first step. We've assumed an acceleration. It's in this direction. All of the masses, 1, 2, and 3, I've sort of done it backwards this time. Maybe it's harder to follow. Mass 1, mass 2, mass 3, tension 1 and tension 2. They're all going to move in this direction. These masses will move. They're all tied together, so they'll all accelerate the same. The system is going to accelerate. Now let's take a look and isolate each individual one. I'm going to start off with mass number 1 here. Draw a little box around there, and I'm going to redraw a green mass here with a box around it. There we are. We've drawn up our green box, our mass number 1, and a box around it exactly like this. We've just blown it up. What we want to do is we want to find the net forces on this, and that's going to create the mass times acceleration. From Newton's laws, we know that the net force, that's all the force net, is going to be equal to the mass times the acceleration. The mass we're referring to is the individual mass, and the acceleration of that mass. Fortunately, all of our masses will have the same acceleration, but they will have different masses. And we have to figure out what the net forces are on that specific box or mass. Here we have a couple of different things acting on this. First of all, we have this acting downward, so that will be m1 times g. Don't forget the 1, and then it's going to have a tension going upward. But this is going to be tension 1. Very careful to put that in there. So let's create an equation for this box and see how it accelerates. Well, we know that the mass 1 times acceleration of the system is going to be equal to, and we know it's accelerating this way, so this one's going to be bigger. So we can go m1 g minus t1. Very important to remember the t1. It's hard to see right there. There it is, t1. This is the first equation. I'm going to take this equation and write it down right here. Give me a second to do that. I've written this equation here. Let's double check it. One of the most common mistakes we make is it's not concept mistakes. It's just dumb mistakes in copying and in simple math. So we always want to double check those things. M1A is equal to M1G minus T1. Okay, got that. So there's the first equation from the first box. We can erase this here, and I'm going to draw up now the second box right up here. Actually, I'm going to do something a little different. Instead of just isolating the second box here, because remember, we're looking for this tension here. So this tension number 1, is acting on this box, but really it controls both these boxes. A little bit of a trick. You want to check that one out. So if we think this tension 1 is going to be operating or controlling or pulling both these boxes, it's as if these two are locked together. We could draw them almost locked together. It's almost as if these two are very close together. There's no actual rope, or the rope doesn't move. So you could think of this as a system here. It is a system with a total mass, a different mass. And this thing is accelerating that. So let's take a look at this here, this system here, which I've isolated with this black dotted line here. And let's take a look at all the forces acting on that. Well, first of all, we would have the force of gravity and the normal force. But since we're not dealing with friction, no friction in this case, we don't need that. Those forces will balance. We'll have the same normal force as the force of gravity, so we're going to ignore that. The unbalanced force is this. So we're going to have this pulling here, which is T1. And what else are we going to have? There's no other forces to the left. So this is the only thing that you have. So we can actually figure out what the acceleration is. So the mass of this system, what's the mass of this system? it's actually m2 plus m3. I'm going to leave them like this instead of adding the numbers, because you're going to see everything fall out with a formula that you've seen before. So mass 2 times mass 3 times the acceleration of this system is going to be equal to T1. T1 is going to control that. We'll take this, we'll transfer this over to here, acceleration. Let's double check it. T1 is equal to m2 plus m3 times acceleration. Good. Okay. We have something already about the system right here. Notice we have T1 in both these equations. Here we have two equations and only two unknowns. We can actually solve for T1 right here before we go on to doing something else. So let's take a look at that and see if we can do that. We have T1 equaling to this. We can take this value of T1 and plug it in for there. So I'm going to write out M1 again. Equation number 1. I'm rewriting it here. M1A is equal to M1G minus T1. T1 is all of this. So I'm going to write all of this in the brackets here. Then I put these big square brackets around here. T1 is all of this. So I'm going to write this in here. It's going to be M2 plus M3 bracket bracket times the acceleration. I have some things in brackets here with a minus sign. I really want everything with the acceleration on that side and everything without the acceleration on this side. So I'm going to take these things, multiply them out. So I'll start off with here M1A, that's this term. And then these two terms, I move them to that side. I'm going to have M2A plus M2A. It's going to be a minus here, so it's going to be plus on this side, plus M3A. Hope my writing isn't getting a little messy here. That would be this term and these two terms. That's all going to be equal to M1G. Now notice these all have a common A. So I'm going to take that out. M1 plus M2 plus M3 all times A equals M1G. Notice here again you have these three that you could take this whole thing and divide over here. I'll do that up here and write it nice and bigly so that you can see this. So this is going to be the acceleration is equal to, we'll have these three things and move them under here. M1G all over M1 plus M2 plus M3. Now, I don't know if this is a G, here, G. Rewrite that G so it looks more like a G. There. M1 times G. Now notice again, we have something similar to what we talked about before. On the top, we have the total force acting on the system. That's really M1G. That's the only force acting on the system, accelerating it in this direction that we assumed. Very important to assume that direction. That's the acceleration. The force acting. This is the inertia of the system. 1, 2, 3. All the forces together are the inertia. Again, if you had seen this ahead of time, you've done these problems a couple of times on an exam, you could probably just pull this out of the air, write this down, and get part of your answer. So we can plug in the values now and see what we get. M1 is going to be 5. So I'm going to get 5 times 9.8 divided by the total. So it's going to be, this and this is 11, plus 5 is 16. This here is about 1/3, so it's going to be about 3. My estimation, about 3 meters per second squared. I'll check my calculator. Amazingly, it comes out to 3.06. Acceleration equals 3.06. Of course, that's too many significant figures. That's 3, you probably have 2, but we're not really concerned about significant figures for this one. In your questions, you probably will be. The answer will probably be 3 or 3.1, depending on whether you have one significant figure here or 2. There's only one listed here. Normally that would be 2.0. Just be conscious of that. In these problems, I may be a little bit sloppy in the answers. It's the system of finding things that I want you to understand. So this is the acceleration of the system right here. Now we only have the first part. We still need to find the tensions. Well, here we have an equation for tension 1. Tension 1, that's this first tension, the blue tension, is equal to M2 plus M3. These two, that's 11. 11 times the acceleration of the system. 3, so I'm just going to 33. Could be 33 point something if we wanted to. So T1 is 33 newtons. This is meters per second squared. We've found T1. We have not found T2 yet. However, we have enough information now to be able to find that relatively easily. So let's take a little isolation on this one over here. I'll redraw the isolated M3 here. Let's say I redrew M3 with an isolation box around it, and we want to look at M3 and see what happens to it. What are the forces acting, the unbalanced forces? There's up and down, of course, not concerned about that. So here we have T2 acting on it. That's the only force acting on it that's unbalanced, that's going to cause an acceleration. What do we know about M2? We know that M3 times acceleration, it's accelerating this direction. We know that because we assumed it, and also because we got a positive answer here. If this answer had been negative, it would mean it's accelerating in the other direction, and you have to do some rechecking, which it wouldn't be in this case. But M3 times acceleration, which we already have found, is going to be equal to tension 2. We have a couple of those things here. We can plug those in. We want to find tension 2. M3 is 2, and this is 3, is equal to 6. So this tension 2 here, tension 2 is equal to 6 newtons. Take a look at that for a second and see if this tension here is equal to 6 newtons and this tension here is equal to 33. Does that make sense? Does it make sense that this one that's pulling 11 kilograms has 33, and this one that's only pulling 2 has 6? It makes sense. It seems to sort of work out. Actually, if you take 33 and divide by 11, you get 3, which is our acceleration. And if you take 6 and divide by 2, you get 3, which is our acceleration. So it makes total sense. This should be much less tension. This is a very simple way. Well, it's not that simple if you haven't done it before. But if you do this one a couple of times using this method, you're going to find it fairly simple. And we're going to go on later on in our next part 4 and work on even more complicated pulley problems. If you enjoyed this video, like and subscribe, and check out our next video. I'll see you then. Bye-bye.